All right, let's go ahead and get started. Thanks for joining, guys. Hope you guys are having a great week so far. Do my obligatory scribble there to test. All right, as always, I can't see the chat, so please just let me know if you have any questions. Feel free to interrupt me. We're going to be doing our little part 2 here for bearing capacity of shallow foundations. So first we'll kind of recap what we talked about on Monday, and then look into some example problems, and then some estimates for subsurface testing, so correlations between SPTs and CPTs. Okay, so yeah, bearing capacity from field tests. This is kind of the new area that helps bypass some of the assumptions a little bit, especially for soil strength and finding the friction angle and the cohesion and all those factors. Being able to get this from CPTs and SPTs, this is really beneficial and helps cut down the analysis time. So just to recap, the two things that we have to worry about with shallow foundations are settlement and then bearing capacity. And the bearing capacity, when I say like the capacity, just think of like the ability for the soil to hold up a certain amount of stress before it will fail in shear. So it's a shear failure technique. So it's failure within the like the surrounding lateral expanse of it. And the things that we have to remember here is that we're always looking at stresses. So we're always going to be looking at the force divided by the area. So the structural load or force here, this would be the size of the footing that we would divide it by that area, and we would get the bearing pressure. And from an actual design standpoint, we would calculate the bearing capacity of the soil, and then we would ensure that our bearing pressure does not exceed that bearing capacity. So that is kind of how we can do that. There's the 3 modes of bearing failure. The first one would be punching that we talked about. We don't really have a design standard for that. Localized is one type, and then generalized is the other type. So for generalized, this is the equations just as they are that we went over last week, and we'll recap them here in last class. The localized, this is when we have to decrease our strength parameters. So this is where we would take 1 or 2/3 of the cohesion as well as 2/3 of the friction angle, and then use those as our design values. For punching, we usually just redesign or improve soil. So it's not really worth going through the additional efforts. We would use a deep pile foundation in that case. So kind of the failure mechanism for shearing that Terzaghi defined in the ultimate generalized bearing capacity is the formation of 3 kind of zones. We have the elastic zone. This is an elastic wedge that forms, and then that essentially pushes on the soil horizontally or at a little angle. And then we see this radial shear zone. And then we see a passive zone that is, again, a wedge that is being formed. So this helps illustrate, because you can see how the depth will help resist this passive zone, this passive wedge here moving vertically. So that's why we say like this bearing capacity, the failure, when you see failure, you usually see like heave or some type of like mounding of the soil next to it, or to the left or to the right. And that's because this passive wedge is essentially uplifting and being pushed up. So if we don't have failure like with depth, like right here, like as I said last class, like if we were like chilling right here, a little soil particle right there, there'd be no shear forming, there'd be no movement. The movement actually forms along this envelope and moves horizontally. So that's why it's important and to consider in the design. So Terzaghi did all that fun stuff and made all these charts and everything. And but the things that you do need to know is that essentially that equation is broken down into three components: a cohesion component, a soil weight component, and then the surcharge component. And when I talk about the surcharge, we're talking about the soil that is above the depth of the footing. So this is where the penetrate or the embedment depth is important when we're looking at our footing. So I was talking about last time. Yeah, you have a question?
Yeah, I just wanted you to look at your camera and see that me, Jeff, and Dennis are all in the classroom.
Oh, look at that. I can't see anything. Nice.
That's all.
Wow, such good students.
Yeah.
This train of thought.
That's funny. Okay. Well, glad you guys are in there and getting used to, or getting some use out of that classroom. That is super small and hot. Okay. Yeah. So here's kind of like a little flow chart to help with these two methods. And as I mentioned last class, there are lots of different procedures and stuff, you know, like Terzaghi and the AASHTO method. These are the two main ones that we're going to be focusing on. So the AASHTO, let's see, what do I have filled in here? Yeah, and but they both have like a similar format. So Terzaghi's method, that's where to find the bearing capacity of the soil, which is QU, ultimate bearing capacity. We have the cohesion term. We have the, oh, thank you. Cody just brought me a sandwich. Isn't she super nice? So nice. We have the surcharge form, and then we have 0.5 of the unit weight. So you have all these factors, but you can see that they're each individually here. So this is, yeah, cohesion. This is the surcharge. And this is the density or the unit weight. So AASHTO method also use this. And oh, sorry, this is also for a strip footing only. So he's derived this whole mechanism for strip footing, which means that the length, what else did she bring me? Oh, blueberries too. I'm getting spoiled here, guys. I need to teach remote more often. Okay, I'm sorry. The strip footing here, this is where the base is greater, or sorry, than 5 times the length, or maybe it's less than. Sorry guys, getting distracted. Just reference the last class to see exactly, but if you'll be told it's a strip footing and that's what you'd use there, and you'd have to adjust it for different types of footings. So you adjust the equation for different footing types. That's from slide 12, the last one. The AASHTO method looks very similar. The only thing they add to it is these shape factors for different footings. So the length to width ratios and all that fun stuff. So we have very similar properties here, but now we have these S subscript whatever. BF is the width of the footing times N gamma, and then these S gammas. So these shape factors, these are for the different footing sizes, different types. And the important thing to remember when you're comparing these two are you would need to use different coefficients, different of these factors. The Terzaghi factors are on slide 13 from last class. And then if you're using AASHTO method, even though they use the same terminology here of N subscript, whatever, they're different actual values. So you'd still need to ensure that you're using the correct one. Now, these were both developed for generalized failure. So for both of them, you would use the same, like if you have generalized failure, then you would use these factors as a function of friction angle, the friction angle. But if you didn't, then you would need to correct them for both of the cases. So if you had localized shear failure, then you would need to adjust this accordingly, both of them accordingly. And then you would plug this C bar back into our main equation. And then you would use this friction angle, this new friction angle, to find these new bearing capacity factors. So we went over that. Use this flow chart as kind of a it's like a decision tree when you are during the exam or homework. The other thing that we went over was the water table. So how the bearing capacity equations will slightly change depending on where the water table is. And the best way of looking at it is summarizing it into 3 cases. Case 3, there's no change. This is where the water table is super deep. So in this little figure here shown on the left, if our depth below the footing to the groundwater table, which is lowercase d, if this is greater than the width of the footing, then this case applies and we don't actually have to change anything. Because remember, the wedge that is actually forming is 45, or whatever the friction angle is here. So most of the time it's going to not be the same height as B. So the soil failure is all moving that way. So case 2 is below the footing, but not that low. So that's where the water table is realistically, somewhere here, like between the depth of footing, but not above the depth of footing. And case 1 would be when it's above the depth of the footing. And so for case 1, geez, I thought I fixed this. I'm sorry. I don't know why these aren't in here. For case 1, we would actually need to change the surcharge value. So this surcharge would equal the unit weight times plus the effective unit weight, or the submerged unit weight. And also this last term becomes the effective one as well. Remember, the effective unit weight or the submerged unit weight, it's the same thing. So sometimes you would say it as this submerged unit weight. This is the saturated unit weight of the soil minus the water, or the unit weight of water. So unit weight of water is either 62.4 pounds per cubic foot or 9.81 kilonewtons per cubic meter. So that's for case 1. Case 2, we don't change the surcharge value, this Q value. Remember, Q in this equation is just gamma times dF. It's essentially the stress, the total stress at this depth. Show it as Q for some reason. But instead, for case 2, we use an average unit weight. So it's the average unit weight below the footing. So we just apply it in this equation. This average unit weight incorporates the section that is saturated or not saturated. So saturated be the submerged unit weight. Okay. Let's see. Okay, I think we did not do this one. This was not an example problem that we did before. So let's go ahead and work on this example problem just so you can have some more. Let me disconnect everything here. Okay. Okay, so we're told that a strip footing with a width of 3 meters is founded at a depth of 2 meters below the ground surface. So strip footing is going to be important. The width is going to be important. The depth below the ground surface is going to be important. And we know it is a soil that has both cohesion and friction angle. So the cohesion is 30 kilonewtons per square meter, and the friction angle is 35 degrees. The groundwater table is located 5 meters below the ground surface. The unit weight of the soil above the groundwater table is given here. So we're asked to determine the following using Terzaghis method, assuming generalized shear. So here, even though our soil is 35 degrees of a friction angle, since we're told that generalized shear is going to be the controlling factor, then this is what we're going to design it against. So we need to find the ultimate bearing capacity, the net ultimate bearing capacity, the net allowable bearing capacity with a friction, or sorry, with a factor safety of 3, and the allowable load per meter length of footing based on the allowable net. So let's first draw this out just so we can get an idea of what we're working with here. So we have a footing that has a width of 3 meters. It is at a depth below the ground, or the ground surface, of 2 meters. So we're just going to say this is capital Q. This is going to be the load that's applied here. This 2 meters is our depth of footing. And we also know that the groundwater table is at a total depth of 5 meters. This is our groundwater table here. So this is at a depth of 5 meters below the ground surface. So make sure to read the problem statements carefully, because sometimes they'll give you the depth up to the groundwater table below the depth of the footing. But in this case, it's 5 meters below the ground surface, so from the top here. So that means, according to our little figure from before, that D, the depth below the footing, right here, this will be equal to 3 meters. So the other things that are given, the soil has a cohesion of 30 kPa, or kilonewton per square meter, a friction angle of 35, and a unit weight of 17.25 kilonewton per square meter. So the first thing that we would do is look and see what type of failure occurs. It's generalized. So since it's generalized, we just use C and phi with no correction or no modification. The next thing we would look to do is find the Terzaghi bearing factors, or N factors, based off of this. So we would then look up Terzaghi's bearing capacity factors. And from this class, that is on last lecture, so 15, slide 13. So since for the groundwater table, our depth to the groundwater table is equal to 3 meters, which is equal to the width of our footing. So that means we are in case 3. Essentially, that means we can ignore the groundwater table. So we don't need to make any corrections for that. That's nice. Okay, so from lecture 15, slide 13. We can find our bearing capacity factors.
Can I have a question?
Yeah, what's up?
On the last slide, when we're doing the example, I thought case 3 is if your base was like larger than or smaller than your depth, but they're the same number.
So right here, greater than or equal to.
Oh, okay.
So I guess that's a lowercase. I changed the notation up. That should be lowercase d, but yeah.
Oh, okay.
Yeah, maybe I shouldn't have used the word super deep. It's super deep in terms of relative to the footing. Yeah, so as long as it's greater than the width of the footing. The depth is greater than the width of the footing. But remember, it's the depth below the footing. It's not the depth from the groundwater or the ground surface.
I see. All right, thank you.
Yeah, good. I mean, good point. Next time I teach this class super deep, I shouldn't. That's kind of misleading. Okay. So looking up lecture slides 15, whatever, for the friction angle and the cohesion, or the friction angle that's given to us. We should get these factors. So these factors here. So when we're finding the ultimate bearing capacity, this is sometimes just called the gross bearing capacity, gross meaning all together, not like deducted down, like kind of like your gross annual income and that kind of thing. So gross, no factor of safety on it. Since it's a strip footing and we're using Terzaghis, what we would use is this equation here. So it'd be 1/2 with no coefficients over the cohesion term. So what we would do is plug everything in. So our cohesion is in kPa, so I'll just keep those units in there. And then our factors are unitless. For the Q, so here what I'll do is I'll calculate Q ahead of time here, or at least show Q. So remember, Q is the unit weight times the depth of footing. So our unit weight of our soil is 17.25, and this is kilonewtons per cubic meter, and then it is 2 meters below the surface. So I'll just plug that in here just so you can see 17.25 kilonewton per square meter times 2 meter. And then we multiply it by our NQ. And the rest of it here, 17.25 kilonewtons per cubic meter times the base, which was what, 3 meters? Yeah, 3 meters times the N gamma, which is 45.41. So if we check our units here, I guess I should have done this here, kPa, everything would be in kilonewtons per square meter. So our QU, our ultimate bearing capacity of the soil, will be 4337 kilonewtons per square meter. So that's our ultimate bearing capacity. So this is no deductions, no factors of safety. What we're saying is based off of Terzaghi's equation, if we apply a stress higher than 4,337 kilopascals to the soil, then the shearing will start to occur in our soil. So we would want to try to limit our footing to be lower than that. As mentioned before, all these factors and stuff, all of the cohesion and the friction angle, this is all made like through sketchy procedures. Like it might not be uniform for every site. So what we do usually is either put a factor safety or look at the net ultimate bearing capacity as well. So the net ultimate bearing capacity, this is accounting for just in case they have to excavate to the footing or something, or we're not having this depth of footing, this stress that the soil above our footing, if we don't have that to help us out anymore. So the QU net, this is our Q ultimate, which is our ultimate bearing capacity, the gross. And then we subtract out the stress at the bottom of our footing. So this Q here would be like right here. So this would be the Q here. And hopefully that makes sense logically. Like erosion might occur, it might like weather down, they might have to install some utility lines in the future or something. So if we're accounting for that stress to be there, or that helping soil to be there in the future, it might not be there, then we don't want to design it specifically so that it might potentially fall. So this equation, we have 4, 3, 3, 7, and then we just subtract out what we did earlier here. 17.25 times 2. And what we get here for QU net is going to be 4,302 kilonewton per square meter. So the net is, again, like erosion, future construction or something. Now you could still apply a factor of safety to it, and oftentimes we still do, just to account for the uncertainty of the theory, the uncertainty of the equation, like or the soil conditions, all of those things. So sometimes we would still apply a net allowable with a factor of safety. So anytime you hear allowable, that is going to be a factor of safety applied. So factor of safety should always produce a lower value. So there's going to be a lot of little subscripts here, but Q allowable net, this will equal the Q net divided by the factor of safety. And you don't have to try to remember these equations. Just when you think of allowable, think of something that is lower than the designed. So this will be divided by this factor of safety. So we divide this by 3. And what we get is 1434.2, sorry, I almost did pounds, kilonewton per square meter, so kilopascals. So let's say we want to go with that design. Like the owner's level of risk assessment is good with this design. They're worth like having to pay a little bit more for a larger foundation or tighter columns to lower the load. So what we would do then is find the allowable load, and the load is going to be a force. What you show this is Q, capital Q. This is the allowable load per meter length of the footing, because remember, it's a strip footing that we were designing. So if we know that lowercase q is a stress, and that is equal to uppercase Q, which is a force divided by the area. But since we're in a strip footing, we don't have a length. So what we're going to do is per unit length. So our area is really just going to be the width times 1 meter, since it's a per unit length. So in order to find that, the Q allowable, we would just, I guess it's net allowable. We would just multiply our Q allowable, lowercase q, times the base, or 3 meters. So essentially, we're going back against the factor of safety, because the math is already there. So our Q allowable, the allowable structural loading on the columns or wherever we're applying to our footing here, this will be 4,302. Yeah, so this would be kilonewtons per meter length of wall. It's not always this case, it's just was because the factor of safety was equal to the width of the footing. So it's not always that case. All right, any questions on that? Okay, let's look at another example. So this one is saying that a square footing, it fails in general shear on a cohesionless soil. So cohesionless meaning C is equal to 0. When the ultimate load reaches 1687.5 kip. So we're actually given an ultimate load. So we're given Q, uppercase Q. The footing is constructed at a depth of 6.5 feet below the ground surface. With these properties, no groundwater counter was encountered. Determine the size of the footing needed using Terzaghis method. So this is actually kind of like an interesting back calculation way. Let's say you have some super old footing or old like foundation, and you can't excavate down to the foundation. It's like 6.5 feet down for whatever reason. But you know that this building actually failed whenever they added something onto it, and it reached like a 16.87 or 87.5 kips. So you could actually back calculate and determine the size that was this footing that caused it to fail at this exact time. So let's just draw a little picture, even though it's much simpler because there's no groundwater here. So we have this footing. We know it's a square footing. We know the Q that it applied was 1687.5. We know that it has a depth of penetration of 6.5 feet. We know the width and the length are unknown, but we know that it's a square footing. So we know that the width is equal to the length. We also know that the groundwater table was not encountered, so it's somewhere super down here where we don't have to care about it. And for the soil properties, it's cohesionless, so it's equal to 0. Our friction angle is 35 degrees, and our unit weight in lovely US units is 110 pounds per cubic foot. So what we're going to do first, we're told to use Terzaghis method, and we're also told that it fails in general shear, generalized shear. So we don't need to change the strength parameters around it all, but what we'll use is just Terzaghis equation for square. So we'll use Terzaghis equation for ultimate bearing capacity and a square. Make sure you're using the right one here. So QU, ultimate bearing capacity, is equal to 1.3 times C times the bearing capacity factor for cohesion plus the term for surcharge plus 0.4 times unit weight times all of those factors. Now we do know, thankfully, we can summarize this a little bit or simplify this a little bit. Since C is equal to 0, this term goes away. So really, our QU is just equal to, and I'm just going to go ahead and put the term here. So the depth of the footing times the unit weight times NQ plus 0.4 times unit weight times the base times N gamma. So we simplify it that way. Okay, so for a friction angle of 35 degrees, our NQ is going to equal 41.44, and our N gamma is going to be 45.41. And we don't need to worry about the cohesion term here. So what we'll do is set up an equation, but what you probably see already is we do not know our base here. So we're going to have to set this equation up and we'll have it as an unknown, but let's go ahead and do that and put everything simplified as far as we can. So QU is equal to 110 pounds per cubic foot times 6.5 feet times 41.44. Then we will add the other term. So that is going to be 0.4 times 110 times base, which is unknown, times 45.41. I have no idea why I put print or brackets there, but whatever. Okay, so everything in here is known, except obviously the bearing capacity equation or the bearing capacity value. But what we can do is just go ahead and simplify this. I'm going to go ahead and do that just to 29.63 times 10 to the 3, and then plus 1998 times the base. And so what we have here is one equation with two unknowns. And we need to find what this base would be. And we are told information on when it fails. So we do know information about this bearing capacity value, but the equation is set up where this is a stress and this is a force, what we know is a force. So going over to the next page, I'll just go ahead and copy this over just so we can have it from before. So QU is 29.63 times 10 to the 3 plus 1998 times the base. This will be equation 1. So what we need to find is some other equation that has QU in it and B in it. So we know that the ultimate bearing capacity is equal to the force divided by the area of our footing. Now, luckily, since it's a square, we know that the area of our footing is just equal to B squared. And we also know the Q ultimate, the force that caused failure, was 1687. And since it's in kips, I'm going to put it in pounds. That would be times 10 to the 3 pounds. Because everything pounds per square foot. So now we have a second equation here. So we still have B and we still have QU, that's unknown, but now we have two equations. So we have two equations, two unknowns. I know that's everyone's favorite thing to do in life. So what we're going to do is we're going to equate 1 and 2. So combine these two here. So just set them equal to each other, right? All we need to do is set them equal to each other and then solve for B. So I'm going to go through this real quick. 1687.5 times 10 to the 3 divided by B squared. That's from equation 2. This is equal to 29.63 times 10 to the 3 plus 1998 times B. So now when we set it up this way, we have B here. Those are our two unknowns. So guess what this is actually going to require? Quadratic. Woo. So yeah, we're engineers, so we would plug this in Excel. We would use Wolfram Alpha or whatever. You wouldn't sit there and do your, I don't even remember it, negative B plus or minus something. But so yeah, we would do this, and what you'll get is a positive and a negative number, right? But obviously, we're talking about a physical footing. So B must be the positive value. So if you were actually doing this out, you would see is equal to our positive B, 6.32 feet. So you would not tell the contractor, okay, we need to purchase or we need to build this 6.32 feet. What you would do, you would recommend something like 6.5 feet by 6.5 feet. this is most likely the type of footing. Yeah, so contractors, you guys who have worked with them already, like, no, they're not always going to be the most precise. This is one footing. You could be doing a multiple footing, so you'd usually just round up to the nearest half foot, or sometimes even full foot, just for the form work to be a little bit easier. Okay, any questions on these two examples before we go to field tests? Okay, so much like everything in geotechnical engineering is still being developed. And one of the ways it's being developed is looking at correlations from these field tests. So field tests are like the borings. These are the SPTs and the cone penetration tests, CPTs. These are always going to be performed at a site investigation. You're always going to go and perform an SPT or a couple CPTs just to ensure that, or just to determine what the type of soil is at your site itself. So the whole thing is okay, if we need to do these tests anyways, why can't we use this data to actually develop like field specific analysis? So it's helpful because, yeah, it's able to estimate properties such as bearing capacity and other properties as well from these field tests. So what they developed here, and I mean, it's still old to us, but this guy here, Bowles, in 1977, he made a really nice geotechnical engineering textbook. He used another guy in geotech who's really famous, Meyerhoff. He used this theory for bearing capacity. So it's a different theory, not Terzaghis, to estimate the Q allowable based on SPT blow count. So the SPT blow count, this is that N value, and this is where we look at the blows per foot. And oftentimes we correct this for 60% efficiency of the machines. So that's where you see this N60. And hopefully you guys remember from Geotech 1, those steps, and we talked about at the beginning of the semester as well, we would correct that. So these equations here are a little funky because they were developed using millimeters. A German guy over here doing this. So yeah, this is all for millimeters. Essentially what you're looking at is the elastic required settlement that you would produce. That is like you're allowed to produce elastic settlement. And so you would use this equation if your width of your footing is less than 1.22 meters. And you'd use the second equation if your width of the footing is greater than 1.22 meters. And so both of these were for square footings only. But there's also fancy charts that apply for these as well, where you could do this as well. The only other thing, this addition here, this coefficient here, FD, this is dependent on the depth of your footing. So what you would do here is you would calculate depth of your footing divided by the width, multiply it by 0.33 and 1, and then add 1. And then whichever one you would smallest or choose, you would choose whichever one is smallest. So choose smallest. So either that or that calculation, or if it's larger than 1.33, then you would do 1.33 as your smallest one. So this one's still used today. There's some software that FDOT has that you would use. I know when I was working at Terracon, Dennis, I don't know if you had to do this at all. They have a whole chart system where you would find the SPT corrected blow count, and then this essential curve, like a curve fitting, where you would plot it on the x-axis, read where it intersects, and then find the corresponding Q net allowable for the y-axis. So something like that. Other charts look at just rough estimates. And so you could also use this if you just need to find something really quickly. This is the standard penetration resistance. So this is just the blow count, the N value for both of them. And what you're looking at is like for the soil type, given the soil type that you're in. So if you were at like 35 and you were in a fat clay, then what you would do, you would read this up, and then you would have this window essentially of assumed ultimate bearing capacity in pounds per square foot. This is ultimate bearing capacity. Then you would need to, apply it to a cohesion or a factor of safety. This is for cohesive soils. So these presumptives, these are Q ultimates. But it helps because these are mainly used for range. So you can, if you're very confident on your soil, you can use the higher range. But again, like for all footing on the top chart, let's say you had a clean or lean clay right here. So essentially what you're saying here is this range is acceptable. So this is at least what you should expect. And we're working on developing these for Florida specific soils. The DOTs and other industries are looking at developing these types of charts for specific type of geologic regions, because it wouldn't make sense to use this chart if it was developed for soils in Dubai to use it in Michigan, something. Okay, well, some of the more technical ones, or more empirically based, I should say, are from bearing capacity for CPTs. So from the CPT, the big benefit of CPT is that it can provide much higher resistance data with depth. And if you think about it, if we zoom in at actually what is happening at a CPT, we have this. Actually straight. I swear by the time I'm like a really old professor, I'm going to be able to draw a straight line. I don't know how people do this. Okay, so this is the cone that's being pushed into the soil. What we actually have with a failure mechanism of this is very similar to shearing. So we have this pushing the soil out this way. And we have little shearing planes that go out both ways. It's very similar to the mechanism of bearing capacity. Because if remember from bearing capacity, we have this elastic wedge that is forming anyways. And then that wedge pushes laterally against the soil. So this test is really helpful for estimating the bearing capacity of frictional soils. So like that type of soils. So what we do here is with a CPT, let me just make sure I didn't, with a CPT, so let's say CPT is being pushed into the ground right here. Gosh. So it's being pushed into the ground. We are measuring the tip resistance. So QC, which is the cone tip resistance. And what we would do is at the depth at which we care about, we would have to take the average tip resistance over a certain value. So what we would do is, depending on the width of the footing, so let's say like this is the ground surface here. So remember, the tip resistance, we're going to have like a whole plot, like something that looks like a bunch of data, that goes like this. And we'll have it, past it as well. So this would be like the QC plot, the cone tip resistance. And it collects data every like 2 centimeters. So we collect a lot of data. Now, the first thing we would need to do is determine what area of the soil is going to experience the shearing. So what we would take, come on. Okay, so what we would take, first we would go down to a depth of whatever our width is, b divided by 2. So we would go to that depth. And then what we would do is then add another 1.1 times the footing width. So the footing width, b is the footing width here. So this range of CPT data here would be what we took the average of. This is the range that we care about. So within this range, that would be where we take the average of QC, the tip resistance. This would be QC average across this depth. So it's dependent on the width of the footing, the width of footing. So once we have that, then we would apply the following equations, and I'm just going to show them here. Based first for clay. So if we have clay soil, if we have a strip footing, then what we would do is find our ultimate bearing capacity by adding these 2.8 times QC average. If we have a square footing, then we would find our ultimate bearing capacity through this equation. Sorry. And this QC average, this would be if our QC average is in tons per square feet. This is like usually how we show these types of, or the QC average. So your ultimate bearing capacity would be in tons per square feet, and you usually put that into pounds per square feet by multiplying it by 2,000. So this would be if you're working with clay, you'd use these two equations. If you have sand, I should say, so tons or square foot, or it could be in kilograms per centimeter squared. I think it's the same value. Tons per square foot is equal to a kilogram per centimeter squared, or very close to it. So if you're working with sand, same thing here. So if we have a foot, then you would find the ultimate bearing capacity through this equation. It's a little bit more tedious. And then if you had a square footing, and your ultimate bearing capacity would be through this one. So these these equations look sketchy, and that's because they are, because they're empirically based for a specific region, and then statistically determined. So you always have to use caution when using these types of footings here. But this is a way that CPTs are being used. And hopefully in the future, again, looking in the future, that we'll have these equations, these empirically developed equations specific to Florida soils. So if you're using CPTs in like the sands in Orlando, then you would have a certain equation that you could apply for that is based off of the data from previously determined bearing capacity failures and that stuff. Geotechnical engineering is just difficult because the failure requires extensive damages. So it's not like we can just produce failures all the time. But as we're getting more failures and more information and more lab testing, then we're able to recreate these a little bit more. Okay, I don't know why I crammed it all on this one, but are there any questions on these correlations? And again, there's lots more out there too that you'll probably come across, but I at least wanted to share the ones that are specific to the PE handbook that you might come across when you take the PE. Any questions? I don't know if anyone else is on. Oh, what is this? This is another one that I didn't. Oh, this is a similar chart, like a similar chart here, but this is used, yeah, kind of old, but for the footing here, you just read it up depending on your depth of footing divided by your base. And then what you would get is a normalized, the Q bearing capacity divided by the QC cone. So whatever their cone tip resistance. So this y-axis, Q ultimate divided by QC average. Okay, if that's everything, then your homework 3 should be posted, or maybe it's homework 4. You should have a homework posted this week. Your quiz there is a quiz this week as well that should be posted as well. I have 2 more exams to grade, so I'll be posting that later this afternoon as well. I'll stick around if there's any questions. If not, just send me an email and I'd be happy to answer. I'll see you guys back in person next Monday.
All right, thank you.
Cool.
Bye.
See you guys. Glad you had a little class. Bye. You should have brought Bowie. Why didn't you bring Bowie to class?